So the big ideas in this chapter mainly revolve around these four things. That algebra is useful for generalizing arithmetic and patterns, and that methods that we use to compute math should be generalized, so we should be able to use the same method for the same basic problem. Children also need to understand symbols, especially those involving equality or even inequality, like greater than, less than, equal to signs, and variables, so that they understand that they're searching for a missing number. They also need to understand functions, that is, equations, tables, and graphs, and how to take those simple patterns and graph them so that it definitely represents a function. The first thing that young children need to understand is that there are connections between numbers and algebra. Look at this example problem. 7 birds have landed in your backyard. Some landed on a tree and some are at your feeder. How many birds might be in the tree and how many at the feeder? If you look at the right, the little sample, this particular child recorded her answers in a table. And you can see that some landed in a tree. That was 2 for the first one. No, it looks like it was 5 for the first one. And then in the feeder, 2. So those two things add up to 7. And then 4 and 3 add up to 7. And 6 and 1 add up to 7. However, let's look at the pattern or the generalization that we can make from this particular table. So it looks like on the left, as the numbers get larger, then on the right the numbers get smaller. Well, that's an interesting thing to realize when you are adding numbers, that you can take away from one side and add to another and still get the same answer. Also, children need to understand place value, and that adding numbers can be found by using a hundreds chart. So actually playing a game where children record their arrows and things on the numbers chart is a great way to get kids to understand patterns and moves. This chart represents the properties in number systems, both addition and multiplication. You need to become very familiar with each one of these, so I urge you maybe to print this slide or to come back and view it, take a picture of it, screenshot it, whatever you need to do so that you will learn these particular properties. These are examples of how properties can be used to teach mathematics. Notice that the properties can be generalized. That means they can be used over and over again. The commutative property, 1 plus 6 equals 6 plus 1. And then the distributive property, that 6 can be divided up into 5 and 1. And then 5 times 8 plus 1 times 8 is the same thing as 6 times 8. Having students prove things through the use of properties is a great way for them to show their understanding of algebraic thinking. Young children also benefit from identifying patterns that don't have anything to do with numbers, like these particular patterns, using cubes, blocks, counters, even color tiles. If you can partner with a music teacher in the school, music also has patterns in various songs, and you can actually have the music teacher support your mathematical teaching by showing the students songs that have an A-B or an A-B-C pattern or an A-B-B-A pattern. It's very interesting for them to see the connections between mathematics and music. Seeing patterns also needs to happen with the older students. Just plain patterns like the ones with the color tiles above need to also be represented in charts in number form. So we want the students to be able to identify what is going on in the pattern and to be able to generalize it and extend it. So we're looking for an algebraic relationship. The study of patterns also extends to finding a rule or a generalization. That's basically what that is. So if we were looking at this particular pattern, we would see that in step 1 there are 4 tiles, and so that's represented on our chart. In step 2 there are 7, and in step 3 there are 10. So what's happening to get from 1 to 4, from 2 to 7, from 3 to 10? We know that we could add 3 to get to 4, but can we add 3 in order to get to 7? If the generalization or the rule does not apply to everything, then it is not the correct generalization or rule. Instead, we have to find another way to get to 4. Well, I could multiply by 3 and add 1. Let's see if that works for the second step. 2 times 3 is 6, plus 1 is 7. Yes, it does work. 3 times 3 is 9, plus 1 is 10. It works. So our generalization, or our rule, then is 3x plus 1, or 3 times our step plus 1. So here are the various ways that children will learn to record their patterns and functions through input-output tables, which we just talked about on the last slide, but they can be horizontal, they can be vertical, however it works, and also through graphing. So we could graph X, of course, horizontal, and Y vertical, and then the children begin to see patterns. This problem shows how linear functions can be used in the real world. The problem says you are asked to build a rectangular pen with 24 yards of fence. So that's how much fence you have. Write an equation to describe the relationship between the width and the area, and write an equation to describe the relationship between the length and the width. So this particular chart, LWA, that you see, does both of those. You can see the relationship between the length and the width, and you can see the relationship between the width and the area, with the width being in the middle. So if we start at the left of the table, we see that if the width is 12, well, the width is going to be twice for it to be a pen. That's 24 yards right there. The length is going to be nothing, so the area will be nothing, because 12 times 0 is nothing. If the length is 11, that adds up to 22. I mean, the width is 11, that adds up to 22. Then the length is 1, but 2 sides of that, there's your 24. But 11 times 1 is 11. That's the area. And we continue to go up, and we can see that as the width and the length become closer to each other, we can see that the area increases. The further apart the length and width are, the smaller the area. It's a very interesting generalization for children to see. So you can see that one way that it's described, the rate of change, and then the slope over on the right side of that, because you have the length compared to the width, and then the length compared to the area. It's important that students know the meaning of symbols. So we have greater than, less than, equal to, equal or less than, equal or greater than. There's several symbols that children need to know. A balance scale is a great way to show that equals is the same thing as balancing two sides of the equation. So if they can conceptualize the equation as a balance, they will learn that both sides of that balance, or both sides of that equal sign, need to be the same value. You can start it with visuals, such as these types of pictures, and then eventually move it to numbers. So let's look at these three different types of relational thinking. First of all, children need to understand that the equal sign means to do something. That's the operational view. So we know that 6 plus 7, it should have something on the other side, and it should be 13. The relational computational view is where the equal sign symbolizes a relation between the two calculations. So you have 7 plus n equals 6 plus 9. So usually children add up 6 plus 9, we know that to be 15, so then they count up from 7 to figure out 7 plus what equals 15. That they actually compute that. Now, the last relational view is the structural view, and that's where the equal sign actually brings to a child's mind that there's a numeric relationship. So if we look at the problem again, 7 plus n equals 6 plus 9, they realize that 7 is 1 more than 6 on the left side, so n should be 1 less than 9 to balance that out. And then they could figure out that numbers do have numeric relationships. Understanding variables is also very important for students. Now, variables can be represented, they're usually represented with letters, but they can be represented with shapes, symbols, whatever. The students just need to understand that you're looking for an unknown. I really like this problem. I took the time to figure it out because it's like figuring out a puzzle. So if you look at it, you know that adding the baseball and the football equals 1.25 pounds. Adding the baseball and the soccer ball equals 1.35 pounds. And adding the soccer ball and the football equals 1.9 pounds. So I figure out from 1 and 2 that that soccer ball actually weighs 0.1 more than the football. So if I go down to number 3 and I put in a football plus 0.1 for the soccer ball, then my actual problem becomes 2 footballs plus 0.1 equals 1.9. Subtract 0.1 from each side and I get 2 footballs equals 1.8. If I divide 1.8 by 2, I get the football equals 0.9. Now all I have to do is plug them all back in, the footballs, and I will be able to figure out what everything is. So in number 1, if the football is 0.9, then the baseball is 0.35. In number 2, if the baseball is 0.35, then the soccer ball is 1. And then in the bottom, the soccer ball is 1, the football is 0.9, and that equals 1.9. Figuring those things out for students can actually be a fun thing. I wouldn't start with decimals because I think that's a little confusing, but starting out with whole numbers would be a great way to begin introducing variables. The videos for this week will help you to understand algebraic thinking a little better. The video on the left is one that was actually done like as a summary to chapter 14 of your textbook. I think that'll be beneficial to you if you watch it before you take the chapter quiz. The other videos are all classroom based, all about numbers and building confidence through problem solving, or about playing with numbers and working with them to find the unknowns. Both chessboard algebra, function machines, and then the elementary math function boxes are ways to teach students about input-output boxes or function machines and how to generalize and make rules. I hope you enjoy learning about algebraic thinking and how it applies in the classroom.